Configuring Genesis for balances. Genesis configuration defines the initial state for things such as accounts, balances, Genesis for custom palettes, and more. This guide explains how to configure the Genesis of a palette with 2 simple storage items. Implement Genesis inside your palette. For the sake of this guide, we'll assume you have a palette, single value, T, and account map, T, for example. The Genesis config code should go after your storage items. Using the palette Genesis config attribute, write the Genesis config struct for your palette. Set the default value for the Genesis config struct. Using the palette Genesis build attribute, implement the Genesis build tray. Copy. This allows you to execute some logic to define how the Genesis config struct places something in storage. Configure your node's chain spec. All that's left to do is to specify what values we want to put in the Genesis state of our chain. We'll assume our palette is called palette something, declared as palette something in our runtime's construct runtime macro. In node chain spec or s, create a constant value of type T, balance to be stored in single value T inside the testnet Genesis method. Note that this step also implies that we have used node template runtime balance imported at the top of our chain spec or res file. Create a vector of accounts to initialize account map T with also inside the testnet Genesis method. Complete the Genesis config clause in the testnet Genesis function. The convention is to use lowercase spelling of the name of your palette in runtime src lib res inside construct runtime. For palettes declared as camel case, for example, the convention is to refer to it as camel case in the test.genesis function. In our example, this looks like in the above code, we're mapping each accounts from accounts to map to an amount equal to value. This pattern is very similar to the balances palettes Genesis config implementation. Using helper functions. Goal: use helper functions inside a palette to improve code readability and reusability. Use cases: reuse helper functions to perform common verify checks across multiple palettes. Sometimes a dispatchable function inside a palette reuses logic that is common to other dispatchables. In this case, it's useful to refactor this logic into its own private function. At other times, dispatchable functions get increasingly difficult to read as the amount of code increases to perform various checks within the dispatchable. In both instances, using helper functions that cannot be accessed from outside the palette are a useful tool to optimize for code readability and reusability. In this guide, we'll see how to create an adder helper that checks for arithmetic overflow and can be reused in any dispatchable. Steps 1. Create your helper function. The helper we'll refer to is called fnadder. It checks that there is no overflow when adding two integers of type U32. It takes two U32 integers, uses checked at no k or to check that there is no overflow. If there is, it returns an error, otherwise it returns the result. Here's what it looks like as a helper function. This would go at the bottom of your palette. Copy. Use it in your dispatchables. Identify the places where you need to check for overflow when performing addition. Use the helper function instead of rewriting the same code. Below is a simple example of a dispatchable that allows assigned extrinsic to add a value to the existing storage value. Example of chain worker, the add price helper function used in this pallet dispatchable.